Hello, chemists. Jolly here again. Let's continue our discussion about proton NMR. And I'm going back to the notes. Let's see, share screen. And all right, this time we're going to be talking about the signal splitting, or it's also called multiplicity. And this one all depends on how many hydrogens are around the peak that we're interested in. Okay, so not the hydrogens that we did the integration on. We're looking at the neighboring hydrogens. All right, you know what? I'm going to put that. It's the neighboring hydrogens, okay? And remember, equivalent hydrogens do not split, okay? Equivalent hydrogens don't split each other. All right, so what kind of shapes are we going to get? Now, remember I told you this will be dependent on like that alkene where they were in restricted rotation. There is actually values associated with this, but I don't go into those much. They're called J values. But let's just talk about the different variations we're going to see. So I'm going to go to my whiteboard, but I'm going to talk about this right here. So go back out to my whiteboard. And that's what we had before, and it's very, very cluttered right now. So I was going to save it, but we will just clear the whole thing. All right, so splitting. A singlet is one line, and that is because there's no neighboring. That's an H. Come on, eraser. Not that it really matters, but GH. So it has no neighbors. Well, how can that possibly happen? Well, we could have a CH3 next to just a carbon, okay? We could have a CH3 next to a carbonyl. We could have a CH2 next to a carbon. Are you getting the theme here? This would make the peak, okay? That would make the peak. But I'm looking at its neighbors, and this neighbor, this adjacent carbon doesn't have any hydrogens, so it wouldn't split. So the only thing you'd see is a singlet. Well, a doublet has one neighbor, and it's all about symmetry. So you would get two peaks that are roughly the same height. An example of this would be a CH2, CH2. Now notice I'm not drawing anything on the other side, so we're just considering only what I've drawn. So if that's the peak, this one has two neighboring hydrogens. And I completely lied to you. It can only have one neighboring hydrogens. This is actually going to make a triplet. So I'm going to erase that. No. Just a CH. Hey, there, that'll give us a doublet because this is the one that we're interested in. This is our peak, and it has one neighbor. So you always have itself or the original peak plus that's how many hydrogens plus how many neighbors will tell you the splitting pattern. So this one is 1 plus 0, so you're only going to get one peak. This is 1 plus 1, so you're going to get two peaks or a doublet. Now let me show you that triplet. Again, symmetry. You're going to have one in the center that's a little bit taller with two on the sides. And this would be the CH2. So this is the one that made our peak in the first place. It has two neighbors, so 1 plus 2. That one would give you a triplet. A quartet would have two roughly the same size in the center. and then two smaller on the outside. And it's very important to look for that symmetry because it'll help you tell the difference between a triplet and a quartet when the spectra aren't very pretty anymore. So this would be a CH2 next to a CH3. So again, this is the one that made our peak, and it has three neighbors. So 1 plus 3 equals 4. 1 plus 3 equals 4. All right, I'm going to delete this out. And we're going to look at 5. That's a pentet. Now, in the proton NMR, they start to get so close that you can hardly tell the difference between them. So pentets, maybe. Anything past that, we usually just call a multiplet. But a pentet has to have 1 plus 4. It has to have 4 neighbors, which would give us a 5. Now, we cannot put a CH4 on a molecule because that doesn't exist. So we are now looking at both sides. So let me show you an example here. 1, 2, 3, 4. Yeah, let's do one more. All right, let's look at this particular molecule. Now there is a plane of symmetry, okay? So we're going to expect 1, 2, 3 peaks. That's a C. We are going to expect this one, A and B are identical. So this one, just reviewing, is 6 hydrogens for the integration. This one is 4 hydrogens for the integration, and this one would be 2 hydrogens. And now I need to know how they would split. All right, so this one right here, if we're looking at that one, that's the original peak. Look on anything adjacent, and so this is 1, 2 plus itself. So this one should be a triplet that integrates for 6. And then we'll talk about location in the next discussion. This one, okay, now it has neighbors on both sides. It has neighbors on both sides. So there's the original peak, plus 1, 2, 3, 4, 5. So 1 plus 5 is 6. So technically that would be a heptet. So let's see, 1, 2, 3, 4, 5, and 6. And that is very pretty, but they're not in the spectra. So we can just call it a multiplet. So when you can't tell how many peaks are in there anymore, just call it a multiplet. So that one is a multiplet that integrates for 4 hydrogens. Now this one, again, I know it has symmetry, but this particular one, what color haven't I used? Let's use pink. Has 2 around it, and so it's peak plus 1, 2, 3, 4, and so that one would be a pentet that integrates for 2 hydrogens. Okay, so that's the way we would go through. And again, these multiplets get very ugly, so anything that you can't see or usually past 5, you can just call it a multiplet. All right, let's do some more examples. Let's delete this. All right, let's put that wonderful alcohol back on there. All right, A, B, C, and D. We're going to go over a couple rules for the splitting. And number 1, heteroatom hydrogens do not split. Neither do aldehyde hydrogens. So this hydrogen right there, that doesn't split. All right, so we're going to combine all of our pieces here. And we have 1, 2, 3 peaks. This one, A would be, look at it. It has 2 neighbors, so that would be a triplet. It's hiding 3 hydrogens. Okay, that's the one we're looking at. So there's one peak plus 1, 2, 3, 4, 5. So say hextet, or this one would be a multiplet that integrated for 2 hydrogens. This one has 1, 2, oh, heteroatoms do not split. So 1, 2, 3, that would be a triplet that integrates for 2 hydrogens. Wait a second. Can you have a triplet for 3 hydrogens and a triplet for 2 hydrogens? Yes, remember the triplet tells you about the neighbors. The hydrogens is the integration that tells you how many were on that particular carbon. And then this one doesn't split because it's hetero. So you get a singlet that integrates for 1 hydrogen, and this is connected to an oxygen. So expect it to be broad because of the hydrogen bonding. All right, let's look at benzene. I'll draw that same one that we had before. All right, how many peaks are we going to have? Let me draw my hydrogens. We are going to have 1. These 2 are identical. Those 2 are identical. There and there. Now for each piece, for the splitting, this one right here has 2 neighbors. So it is going to be a triplet that integrates for 1 hydrogen. B also has 2 around it, so it should be a triplet. But remember, the 2 B's are identical, so that integration will be 2. And I'll use the one up here since it hasn't been written on. And for C, there's no hydrogen right here. So it only has 1 neighbor. So it should be a doublet that integrates for 2 hydrogens. All right. This one, this one right here does not have a hydrogen. So the only thing it has is that one. So 1, 2, 3 plus itself. That one should be a quartet that integrates for 2 hydrogens. And last but not least, that one has 2 neighbors. So 1 plus 2, this should be a triplet that integrates for 3. A triplet that integrates for 3. Okay. Now notice none of those were heteroatom hydrogens, so they all participated in the splitting. Let's do an aldehyde. All right. In this particular picture, those 2 are identical. So those would be A. There's a hydrogen right there, so that would be B. Carbonyls don't have any. And this one would be C. So we'd expect 3 peaks. Go back to red. This one right here has 1 neighbor. Okay, so I'm just going to look at this location because they're going to be identical. So itself plus 1. This should be a doublet, but it's not going to integrate for 3. It's going to integrate for 6. So imagine how many hydrogens are the boxes hiding, and that is a total of 6. So that is a doublet that should integrate for 6. If we're looking right here, okay, now we're looking at its neighbors, which are here and here. So it's self plus 6. We're just going to call that a multiplet, but it's only integrating for 1 hydrogen, so it should be tiny. And then this one should be a singlet that integrates for 1. It does not participate in the splitting. So even though it's connected to an adjacent, an adjacent carbon right there, it is an aldehyde hydrogen, so it does not participate in splitting and it does not split itself. All right, and that's pretty much multiplicity. Now, I did talk about that J value. So let me see, delete this page. And just really briefly, I was talking about the symmetry on these splitting patterns. Well, if you actually measure this difference, that's called a J value. There's literally a difference, and they can be read by the nicer NMRs, and you can determine something about the splitting looking at those J values. I don't really go that deep into it, but if you take any future classes, you can really glean some really good information from those J values. So just so you know, yes, it's all about the number and the splitting and the neighbor and the distance. But for us, we're just going to call it singlet, doublet, triplet, quartet, pentet, and then of course anything past that, we would just call it a multiplet. I do have to beware you that you can have doublets of doublets. What? Let me go back to that benzene. We said, let me see, A, B, C, D, and E. We said this one was going to be a triplet for one hydrogen. We said this was going to be a triplet for one hydrogen. Oh, sorry, for two hydrogens. And this one was going to be a triplet for one. No, this one would be a doublet. This one would be a doublet for two hydrogens. Now that looks beautiful, except these are all benzene. And so they're all similar environments. So they might fall on top of each other. So we might find something that looks like, particularly this one, it might look like a triplet of triplets. Or maybe these two combining, that could look like a doublet of triplets. DOUBLET of triplets. Now, those words probably don't mean anything until you see a spectra, but we're going to look at what we would see. All right. So in the benzene location, let's consider A. So we're going to make a pretend spectra here. Now, we don't know the location yet. So we know that benzene is going to be really close on top of each other, but we don't actually have a number yet. So I need a triplet that integrates for one. All right, so there's a triplet that integrates for one. I also need a triplet that integrates for two. And make that one twice as high. Okay, that's, oh, we have an alarm going off. Sorry about that. I unplugged my microphone, sorry. Yeah. All right. So notice how those are kind of on top of each other. Oh, and then we're supposed to have a doublet in there too for two hydrogens. So we have a doublet in there. Usually you get a mess for benzene. Well, the computer, remember, those are so close together that they might split each other and actually look more like a triplet of triplets. Let me see. A doublet of doublets is easier to show you. So a doublet of doublets would look something like that. A triplet of triplets, remember these are pretty, would look something like that. On benzene and on alkenes, they're so close together that they kind of don't know which ones are splitting, but you can tell by the J values, but again, we're not going to go that detail. So when we, have our discussion about benzene a little later, we'll really worry about those triplets of triplets, and mostly we'll just see it on the spectrum. I'm going to pull up the handout. Now these right here, oh, aren't they perfect? Okay. Ooh, now I know it's tiny. Roll it up. Okay. But there, it integrates for two. What would we call that one? Okay. Now, it's all about the interpretation, and the spectra are not beautiful, so we don't fall in love with anything, but you make your best guess. But this one right here
1, 2 on the outside, and then 2 that are roughly the same size in the middle. So that one definitely looks like a quartet. Where this one, there's 1 in the center, and there's 2 on the outside. So that one's definitely a triplet. And we just can't decide, is that a really fat singlet, or could it possibly be a doublet? We'll put a note to yourself for both. Okay, so that's how we're going to determine whether they're singlets, doublets, triplets. And I'm going to go to a different screen that I can write on. And where do I want to go? And I just want to be able to write on the handout. And the chemistry, first semester, problems. Yes, I have so many layers. Handouts, and I want handout number 7. Okay, that was a long way to get to the handout. Sorry about that. All right, so let's talk about what we do know. What can be found, of course, the number of peaks, the splitting. So everything I told you is right here, kind of in a summary. The integration. So the last thing I have to talk about is shift, but I wanted you to see some examples of what I'm talking about. All right, so I promised I'd come back to that benzene. I have drawn these for you on the handout. So there's a plane of symmetry in a monosubstituted. Okay, so it has one thing that's been attached to it. So you're only going to get 1, 2, 3 peaks. But for A, okay, oh, let me see. Yep, this one right here, you're going to have 1 hydrogen there, 1 hydrogen there, 1 hydrogen there. So that's going to be a doublet that integrates for 2. This is going to be a triplet that integrates for 2. And that will be a triplet that integrates for 2. And I've shown that for you right there. Okay. All right, if you have di substituted and they're the same, okay, notice the A and the A are the same. That plane of symmetry goes right there. And so A is only going to be a doublet for 2 hydrogens. Okay, equivalent hydrogens do not split each other. Do you notice the B and the B? Those are identical to each other. And so they're not going to split each other. So the only one that's going to split it is its neighbor. So that's a doublet for 2 hydrogens. Okay, and that's what I'm talking about, a doublet of doublets. You would see something, okay, not quite that pretty, but you would see that nice symmetry in your proton NMR. All right, what if they're one, away from each other? So there's one in the center. We'd have 1, 2, 3 peaks. Well, this one's all by itself, so you would see a singlet for 1 hydrogen. And then this one has 1 neighbor, so you would see a doublet for 2 hydrogens, and you would see a triplet for 1 hydrogen. Remember, I'm talking about C here, and B's on both sides are different. Where right here, the B was trying to split another B, and equivalent hydrogens don't split each other. So there's what you would see. Now this one's a little harder. So basically you're going to see this nice tall peak, okay, this singlet, and then you're going to see a doublet somewhere, and then you're going to see a triplet somewhere, and the triplet's going to be a little smaller. So you're going to see something like that, but the key is usually that singlet sticks out, right? That singlet sticks out. Now, what if they're exactly opposite each other and identical? I like this one because you have perfect symmetry. A's don't split A's. So you are going to have 1 singlet that integrates for 4. Well, what about di substituted, but they're not the same? So notice this time the A is different than the Z. So this one and this one are no longer identical. So you're going to get 1, 2, 3, 4 peaks. Here, okay, you're going to get 1, 2, 3, 4 peaks. And here you will get 2 peaks because this side of the molecule is not the same as that side of the molecule. And before I go further, These actually have substitution patterns names. So let me draw a little picture for you. So if we have a reference, which is A, to the right and left of A, this is called ortho. So if you're right next to it or adjacent. If you're one away, ooh, let's use lime green. If you're one away, that is called meta. And these are just visuals. So if I say it's meta substituted, you know they're one away. If I say ortho, they're right next to each other. And if I say para, they're opposite each other. So ortho, meta, para, and then meta, and then ortho again. Those are just terminologies dealing with benzene specifically. All right, that takes care of the splitting patterns without doing examples. All right, until next time, Jolly out.